Hey kids, welcome to your Algebra 2 video on systems of linear inequalities. So we're going to jump right in, get this over with. I've already recorded this entire video once, but it didn't take or something, fun technology glitches. So I'm just going to get this done and you can start graphing some systems of linear inequalities. Okay, definitions. A system of linear inequalities is made up of two or more linear inequalities. And you can see that right here. You've got this one, which is y is greater than negative 3x plus 5. And then you've got this one right here, which is y is less than or equal to x minus 2. The solution of the system should be is, not if. Is an ordered pair that makes all inequalities in the system true. So that would be all of the ordered pairs that you can find in this double shaded region right here. Let's change our tool we're using for that. Oh, look, a finger. Ta-da, here, this region right here. So not here, not here, not here, this region right here, the overlap. And you notice that they like to use two colors or two different types of shading. So for example, you might see horizontal shading on this one, and then see vertical shading on this one, and the cross-hatch section right here. That's the section that's double shaded. So that's your solution set. And all of the ordered pairs in that section are included. Notice that would include ordered pairs on this line right here, this line, but it would not include ordered pairs that are on that line because it's a broken line. So those points don't make the system true. Let's take a look at another example. So we're going to graph this system. We have y is less than 2x minus 3, and 2x plus y is greater than 2. And we're going to graph the two lines and the shading appropriately. So let's start with the first line. I'll graph it in blue. So y-intercept of negative 3 and a slope of 2. So rise of 2, run of 1, point. 2, 1, point. 2, 1, point. And remember just to draw dots. Do not draw a line yet. You may not have determined whether or not you can draw a line. So I'll put the arrows on the end, and it's just y is less than, so that is a broken line. So we're going to kind of make these dots have little tails on them, make it look like a broken line. And finally, we are less than. So we are shading from here down, less than, so below the line. And remember that you could take like a 0.00 and test it. And if you do that, you're going to have 0 is less than 2 times 0 is 0 minus 3. Is 0 less than negative 3? No, it is not. So 0, 0 here, not included. It's got to be this side. So let me go ahead and do my horizontal shading lines so you can see that there. All right, now the other line needs to be solved for y. So let's do that one in red. So we're going to subtract 2x from each side. Make sure you can see my minus sign there. So y is greater than, remember to write it negative 2x plus 2, positive 2, so plus 2 there. So negative 2x plus 2. All right, y-intercept of 2, slope of negative 2, down 2, right 1, down 2, right 1, down 2, right 1, down 2, right 1, and the same go in the other direction. Broken or solid? Yes, that's right, it is broken. So we'll go ahead and put our little tails on our dots to make this a broken line, like so. In which direction are we shading this time? Well, this time, because it's greater than, we're shading above the line. So let me take my color and I'll do vertical line shading here so we can easily see our crosshatch section. And that's funny, it kind of turned out the same as our first example, which is completely unintentional. But you can see here that you have your double shaded region, excuse me, your double shaded region, which is your solution set for the inequality. Okay, onward to another example. Okay, so this time, I have 2 lines to graph. So why don't you pause it, graph it, and then come back and take a look at your handiwork and see how it turned out. But I'm going to jump in and go ahead and do mine now. All right, so let's do green for the first line. So I'm going to need to solve this for y. I got 3y plus x is greater than or equal to 9. So we're going to subtract x from each side. 3y equals negative x plus 9. Everything needs to be divided by 3. Now let's remember what this means. Uh-oh, look what I did. You see what I did? I changed it from an inequality to an equation. That's very dangerous. Pay attention, Miss LeCompte. All right, so y is greater than or equal to. How do I write negative x over 3 as a number times x? Well, we've been working through this, and this is something we should recognize now. The 3 is in the denominator, and we could put a 1 between the negative sign and the x. So that is negative 1/3 x, and then plus 9 over 3 is 3. So y-intercept of 3, slope of negative 1/3. Down 1, right 3, down 1, right 3, up 1, left 3, up 1, left 3. Y is greater than or equal to solid line. And it's greater than, so above the line. Very clear, very easy to see that that's above the line. Awesome. All right, next one. Let's solve this one for y. Now, conveniently, this one, not as much work to do to solve for y, so I won't need quite as much space, which is good, because I don't have enough, really. Dividing everything by 3, very similar outcome to what we had with the first equation. Again, that's negative 1/3 times x, and then it's minus 4. So I have a y-intercept of negative 4, and another slope of negative 1/3, so our lines are parallel. Interesting. What is that going to mean about our line? Now this one, not solid, broken. So I'm going to put my dashes in. And this one is also greater than. So it's y is greater than. So we're going to, let's do horizontal lines like so. So what happened there? Where's our solution set? Well, what it turns out is that it's the solution set that's actually just for the green line there. Let's switch colors to make sure that it's clear what I'm talking about here. It's just the one for this green line here because that solution set lies within the solution set for the other inequality. So you would just have that one. Now, ponder for a moment, what would have happened if this one, this inequality here, had been a less than? Well, we would have been shading below the line, and you would have had this empty space in between, which would have indicated a no solution result. So notice when they're parallel lines, you can end up with a weird-looking solution where it's really just the same as the solution of one of the inequalities, or you can actually even end up with no solution at all. You could also have had they gone opposite directions, you would have had the entire coordinate plane. And that would be all the possible points of the entire coordinate plane. So you've got similar possibilities to what you have with lines. We won't see very many of those anomalies. Most of our systems will look like the first two. Next example. You want to build a fence for a rectangular dog run. You want the run to be at least 10 feet wide. The run can be at most 50 feet long. You have 126 feet of fencing. What is a graph showing all the possible dimensions for your dog run? Well, the first thing we've got to acknowledge here is what are we using as variables? So let's start with identifying those variables. Let's make x the width of the dog run, and y is going to be the length of the dog run. Okay, you're building a fence for the whole thing, and you have 126 feet of fencing. That means that the perimeter of your rectangle has to be less than or equal to 126. Now, how do you find perimeter of a rectangle? Well, you've got x, and you've got y and y. So you have two x's and two y's, and that sum has to be less than or equal to 126. Okay. X can be at most 50 feet long. Excuse me, y can be at most 50 feet long. The run can be at most 50 feet long. So the length, y, is at most 50. That means it has to be 50 or smaller. But at the same time, okay, so actually, hold on here. Let's do something real quick. Can I erase that? Oh, good. Let's make it a compound inequality. Because yes, y has to be less than or equal to 50, but it also has to be greater than or equal to something else. Now, what would be the lowest limit for what you can have is the length of the dog run? Well, you could be 1 foot. It'd be a very unpleasant dog run for the dog. It'd basically be just running back and forth down a long hallway, but you could be, it could be a length of 1, or actually a very short hallway if it's 1 foot long. Anyway, can't be negative either, can it? So the low end is 0. And we're going to be able to do the same kind of thing with the next one. It says not the next one, should be actually previous, but you want the run to be at least 10 feet wide. Well, x is going to be at least 10. We don't have an upper limit for the x. We just know that it's got to be at least 10. And so now I have 3 inequalities that I can use to graph and to figure out my situation here. What I am also going to do, and we'll see this on the next slide, so you don't have to start sketching a whole graph, it'll be on the next slide, is that I'm not going to have any information in any of these 3 quadrants. So when I actually graph this, I'm not going to be worried about having anything in the negative quadrants at all for x or y. Okay, so my inequalities again, just to review here, were 2x plus 2y is less than or equal to 126. Oop, almost wrote 8. Hold on. Fix that. 126. And y is less than or equal to 50 and greater than or equal to 0, which is one of those things that kind of goes without saying in this. And x is greater than or equal to 10. The width had to be at least 10, and the length was no more than 50 to fit in the space that the student has. So I'm going to set up my graph, and let me just take a second to do that. So I'll pause it and set it up. So hold on just a second. And here we are. So our graph is all set up. I counted by tens. A lot easier to count by tens here. It's going to be a little bit more difficult when we get to the graphing part for some of it, but that's okay. If we take the first equation, which I'm going to graph in red, and we solve it for y, we end up with y is less than or equal to negative x plus 63. And that one's actually going to be kind of a pain in the butt to graph, so let's go ahead and graph that first. Okay, so let's start off by finding a good ordered pair that's on that graph, because what we're not going to have is some nice happy whole numbers here, because I counted by tens the way I did. So let's start with actually the y-intercept would be fine. Let's start with that, which is 63. So here's 60. Here's 65. So here's 60, here's 65. Where's 63? Well, it would be about there-ish. I'm kind of exaggerating because it's kind of hard to graph it otherwise. Down 1 over 1 for the slope, which actually I know that that's not 1, it's 5. But remember, if I go down 1, right 1, okay, that's the same thing as going down 5 and right 5. It's the same ratio. Down 1, right 1 is the same as down 5, right 5. Same ratio. So that point goes those points go all the way down. So that means that I can just skip down a few, just so I have kind of a guideline for drawing this. And it means that it's going to cross right around 63. Okay, and that is going to be a solid line, so let's go ahead and draw that solid line. And we know that we're talking about the values below that because it's a less than. But keep in mind that when we're talking about that, we're talking about values that only go down to the axes, to the left to the axis and to the and down to the axis, because you can't have negative values here. Okay, we established that on the previous slide. Okay, let's try this next one. We'll do it in blue. As our y is between 0 and 50. So a horizontal line, because that's, remember, hoi vux. Think back to hoi vux. Horizontal lines, because it's y equals, they're both solid, and we shade in between them. So this is the region that would be shaded there. So at the moment, we have this lovely triangle. Actually, no, excuse me, quadrilateral. Trapezoid, in fact, to be specific. What kind of quadrilateral? Let me indicate what I'm talking about here. That's trapezoid. Funky looking trapezoid, but it is. Okay, last one we'll do green. This is our x is greater than or equal to 10. This is a vertical line at x equals 10. And it's shaded because it's greater than. That will be shaded to the right. So we get this shading. And we end up with a slightly smaller trapezoid that goes from here down here. And these are all the values that would work for the size of the dog run. So say that they asked you to pick 3 sets of the three what am I trying to say? 3 sets of ordered pairs that would be the values, the length and the width of the dog run. Oof, this comp's having trouble thinking today. Must be how cold it is. Okay, so what would be some values? Well, let's say if x is 20, then y could be 40 or 30 or 20. Let's do 40. So it could be 20 feet wide and 40 long. Sorry for the messy writing. What about a different value? Well, say x was 30. It could be 30, 30. So you could have that. You could have 30 feet wide, 30 wide, and 30 long. And how about a third ordered pair? Now some of these really wouldn't be very convenient, but maybe 50 wide and 10 feet long. That's a little strange, but it works. I mean, it still gets you what you need for the space that you need. And that was the whole idea, is what are our possibilities? What are the possible values? Let's do 40, 20. There's another one. 40 feet wide. Whoop. Wide. And 20 long. Okay, so there's 3 different values, 3 different ways to do it. So this would be a real way you can use a linear inequality. And yes, it's the kind of thing that that you know, you could probably figure out without the inequality, but some of us really like to have a visual, and that visual aid helps us make decisions based on what we need to figure out. Thanks for watching. Shoot me an email or an Edmodo message if you have any questions. There'll be an extra practice link with the video. All right, guys, see you in class.